Hi, in this video we're going to look at finding all this information that we can find from the function and its first and second derivative to determine all those different things we can find from that and sketch a graph. Alright, so we've done some different problems where we've done kind of pieces and parts of this, but this will be the first one where we've done all of this stuff together. So even if it doesn't tell you to, first things first, you should think about finding the domain of the function. And so several things to think about: denominators, I don't have any of those; radicals, I don't have any of those; logarithms, I don't have any of those. All right, so our domain is going to be all real numbers, or if I want to write that in interval notation, negative infinity to infinity. So that's something I can tell from the original function. Other things I can tell from the original function are x, y points. So if I plug in some x values and get some y values, I do that in the original function to get points. I can also use x, y values to think about limits of this function. So we might do that at the end here, but those are some things that I can find from the original function. All right, I am going to go ahead and find the derivative and put that here. And then we'll talk about what we can find from the first derivative. So I'm going to need to use product rule and a little bit of chain rule to do that derivative. So derivative of the first function, derivative of e to the 2x, that's where I'll have chain rule. So I'll have derivative of e to the 2x is e to the 2x times the derivative of what's inside the exponential function, so times 2. Derivative of the first times the second plus the first function times the derivative of the second function. All right, so there is our first derivative. Before I take a second derivative or do anything with that first derivative, I'm going to want to clean that up. So there's a little bit of distributive property I can do. I'm going to think about distributing this 2e to the 2x through to both of those terms. And then I'm also going to distribute the e to the 2x through to both of those terms. After I do that, you might notice that you have some like terms here in the middle. And actually, I'm going to go ahead and, as I rewrite this, put the x squared and x in front of the e to the 2x. It doesn't really matter what order I write it in, but I just think it looks a little nicer to put the x squared in front of the exponential function. All right, so I have the 2x squared e to the 2x term. That's the first term. And then when I add these two middle terms together, I have 2 plus 2 is 4, x e to the 2x. And then my e to the 2x term at the end. All right, so now if I'm going to take a second derivative or set this first derivative equal to 0 and solve for x, there are some other things I might want to do. It kind of just depends on what you're going to do next with it as to what you choose to do. I am going to go ahead and notice that I have a common e to the 2x that I can factor out. And whether I do that now or later, at some point, I'm probably going to do that before I find my critical points and or my second derivative. All right, I'm going to go ahead and find the other things that our first derivative tells us though. So first of all, critical values or critical points. So I'm going to think about where the first derivative does not exist. So I'm going to look up here at my first derivative and think about, are there any places where that thing would be undefined? There aren't any. And then I'm going to think about where the first derivative is equal to 0. So I'm going to have 0 equals and set my first derivative equal to 0 and solve for x. Okay, so this is already factored. If it weren't already factored, that would probably be my first step, is to factor it, because if I have an equation that is factored and equal to 0, I can then set each factor equal to 0 and solve for x. E to the 2x is never equal to 0. E to any power is always positive, so that one just gives me no solutions on that part. When I set the second factor equal to 0, it's quadratic. It doesn't obviously factor, so I'm going to just jump right to quadratic formula. So I'll have x equals negative b plus or minus square root of b squared, so 4 squared is 16, minus 4 times a times c. So 4 times 2 times 1 is 8, all over 2a, so that's 2 times 2 or 4. I'll just go ahead and write 2 times 2 there. All right, and then I want to go ahead and simplify this. I'll probably want a decimal approximation also at some point. I'm going to notice that I can do 16 minus 8 is 8, and so I can rewrite this square root part as square root of 8. One thing that you want to be careful about is canceling. Sometimes I see students notice that there is a 4 on the numerator and a 4 on the denominator, and they try to cancel those. If remember that the 4 on the denominator is also a denominator for the square root of 8 term, so I can't just cancel those that are in the front. I do have a couple of options for how I might want to simplify that though. I could take the negative 4 that is the first term on the numerator and put that over the 4 that's on the denominator and then reduce that individually. Or I can factor something out of the numerator and cancel. I'm going to go ahead and split this up so that I have the negative 4 over 4 and then the square root of 8 over 4. The square root of 8 though, as I rewrite that down, I'm going to realize I could simplify that some more. I can think about 8 as 4 times 2. So square root of 8 is square root of 4 times 2 or 2 square root of 2. Okay, and then I can reduce each of these individual fractions. So negative 4 over 4 reduces to 1, and 2 over 4, I can cancel a 2 out of those, and that leaves a 2 on the denominator. So I have negative 1 plus square root of 2 over 2, and negative 1 minus square root of 2 over 2. I will at some point want some decimal approximations for those, so I'm going to go ahead and write them down here. Just get out your calculator and do negative 1 plus square root of 2 over 2. You get about negative 0.29. And then negative 1 minus square root of 2 over 2, I get about negative 1.71. So those decimal approximations will come in handy when I want to plot some points. Okay, so once I found my critical points, generally what we do next with that first derivative is make a sign chart to help us determine where the function, the original function, is increasing and where it's decreasing. So I'm going to make a sign chart. I'm going to put on it any places where I have domain breaks. I don't have any of those on this one. And then my critical values or critical points. I'm going to put the exact value on here, but the decimal approximations will help me think about which one's bigger and which one's smaller. And then also when I put them on the graph, where I'm going to put those points. I'm going to test the sign on my first derivative. And so this is where a calculator is going to come in handy. I want to plug in a number bigger than negative 1 plus square root of 2 over 2. So remembering that that's about negative 0.29, I could plug in a number like 0 or something like that. I'm going to plug it into my derivative, which I have right here, the factored form. So when I plug in a number like 0 or something 1, something that's just bigger than negative 0.29 into that derivative and then check the sign, you're going to get a positive for that one. So that tells us that the function f of x is increasing on that interval. All right, when I plug in a number between my two critical points, and again, this is when you're going to want those decimal approximations to think about that. So a number like negative 1, for example, would be a good number to plug in between those. Plug that into your first derivative, and you should get a minus in that region. So that tells you that the original function is decreasing in that region. And then a number left of negative 1.71, so like negative 2 or something, plug that into your first derivative. The first derivative should turn out to be positive there. And so that tells you that the original function is increasing. And these arrows are helpful to kind of visualize what's going on. The function's increasing and then decreasing and then increasing. So you can see that you have a high point. This would be the location of a maximum, a local maximum, and then a low point. That would be the location of a local minimum. All right, so I'm going to go ahead and write down kind of how you might be asked to give your answers. You would say that the function f of x is increasing on, and then you're going to be asked to write some intervals. So I have two separate intervals. One of them that is left of x equals negative 1 minus square root of 2 over 2. So that would be the exact form for that interval. If decimal approximations are what you want, you could use that decimal approximation there. And then I also have increasing on another interval from negative 1 plus square root 2 over 2 to positive infinity. So I'm just using what I have in my sign chart above to help me answer that. The function is decreasing when we are between those two x coordinates. So from negative 1 minus square root of 2 over 2 to negative 1 plus square root of 2 over 2. And then I have a local or relative maximum. And the relative maximum, remember that our maximums are really y values, but that occurs at an x coordinate. So I'm going to go ahead and write this as a point. This is how our online homework usually asks us to write that. xy is equal to, and actually I'm going to use some decimal approximations here. So our maximum was at -1 minus square root of 2 over 2, or approximately -1.71, and then I'm going to come back and fill in that y coordinate there. And I have a relative minimum at our other critical point that we found, so about -0.29, and I'm going to come back and fill in that y coordinate. All right, so the reason I'm going to come back and fill in those y coordinates is, remember, if you're looking for points, xy points, where do you get those from? You get those from the original function. So I'm going to go back up over here to the original function, and I'm going to plug in those x coordinates so that I get y coordinates. The reason I'm plugging in those x coordinates is because of the work I did with my first derivative, but where I'm going to plug them in to get xy points is into the original function here. All right, so this is where you're going to want your calculator, and again, you could have xy values in exact form. They're going to involve all kinds of ugly radicals with square roots of 2, or you can get a decimal approximation. That's what I'm going to use here. So when I plugged in the -1 minus square root of 2 over 2, I got about 0.04, and these were approximate. And when I plugged in the -1 plus square root of 2 over 2, I got about -0.12, rounded to 2 decimal places. All right, so those are the y coordinates of those points I was looking for over here. And if you look at the values of these y coordinates, you notice that they're really, really close to 0. And so that actually points out part of why we actually want to use calculus to answer these questions. Because if you just looked at a graph on a graphing calculator or whatever other kind of graphing utility, these would be really hard to see. These points are both really close to the x-axis. Their y coordinates are really small, and they're really hard to see that the function is doing anything there. So kind of points out why we would want to use the calculus to find all these things rather than just typing everything into a graphing utility. Okay, let's go ahead and find the things that the second derivative tells us about. So I'm going to find my second derivative, and I'm going to do that by using this first derivative, the form that I have circled here that's got the e to the 2x factored out. All right, so I'm going to need product rule and chain rule again. All right, so derivative of the first function, derivative of e to the 2x will be e to the 2x times the derivative of what's in that exponent, so times another 2. Derivative of the first function times the second function plus the first function times the derivative of the second function, so times the derivative of the 2x squared plus 4x plus 1. So I'll get 4x plus 4. Okay, so kind of a messy second derivative, but I'm going to clean that up and simplify it so that I can then do all the things that I did with the first derivative, but doing them with the second derivative. Okay, so this 2e to the 2x, I'm going to distribute through to each term there, and same with the e to the 2x, and then I'm going to combine like terms. So I'll have 4x squared e to the 2x plus 8x e to the 2x plus 2e to the 2x. That's all from the distributing through on the first parentheses. And then on the second parentheses, I'll have 4x e to the 2x plus 4e to the 2x. All right, I have some like terms here. I have a 2e to the 2x and a 4e to the 2x that I'll be able to combine. And then I also have an 8x e to the 2x and a 4x e to the 2x that I'll be able to combine. So when I combine like terms, I'll have 4x squared e to the 2x, and then plus 12x e to the 2x, plus 6e to the 2x. And because I'm going to set that equal to 0 and solve for x, I'm going to go ahead and factor out what I have in common. I have an e to the 2x that's in common. I also have a common 2 that goes into 4, 12, and 6 that I can factor out. So I'm going to go ahead and factor out the 2 and the e to the 2x. So I'll be left with 2x squared plus 6x plus 3. All right, so there's my second derivative, and then I'm going to go ahead and find my hypercritical points, hypercritical values, where the second derivative does not exist or is equal to 0. So I don't have any places on this one where the second derivative does not exist. I do have some places where the second derivative is equal to 0 though, so we'll set the second derivative equal to 0 and solve for x. Okay, so again, I have an equation that's factored and equal to 0, so I can set each factor equal to 0. So I have 2e to the 2x is equal to 0, or 2x squared plus 6x plus 3 is equal to 0. All right, from this first part, 2e to the 2x equals 0, maybe you divide through by 2, and then you have e to the 2x equals 0. But e to any power is never equal to 0, so I don't get any from that. For my second one here, I'm going to go ahead and use quadratic formula. So I'll get x equals negative 6 plus or minus the square root of 6 squared, that's 36, minus 4ac, so 4 times 2 times 3. So that will be 4 times 2 is 8, times 3 is 24, all over 2 times a, so 2 times 2 is 4. All right, so I'm going to go ahead and simplify this radical. 36 minus 24 is 12. So this part can become square root of 12. I'm going to split that 4 again on my denominator. So I have negative 6 over 4 plus or minus, and then I have square root of 12 over 4. Maybe you notice that square root of 12 can be thought of as square root of 4 times 3, which is 2 times square root of 3. So in that second fraction, instead of writing square root of 12 over 4, I'm going to write 2 square root of 3 over 4. And then there is a little bit of reducing I can do. In this first fraction, into 6 and 4, 2 goes into both of those. So I'm left with a 3 on numerator and 2 on the denominator. And in the second fraction, 2 goes into both 2 and 4. So I'm left with a 1 square root of 3 on the numerator and just 2 on the denominator. So I get negative 3/2 plus or minus square root of 3 over 2. This is my hypercritical values, and then the next thing we're going to do is put those on a sign chart, just like we did for the first derivative with our critical values. This is where maybe you want some decimal approximations. The one that is negative 3/2 minus square root of 3 over 2, that one's going to be the smaller one. That's about negative 2.37. And then the one that is negative 3/2 plus square root of 3 over 2, that one's going to be bigger, and that one is about negative 0.63. All right, so I'm going to test those by plugging values on either side of those split points into that second derivative to determine the signs on my second derivative. Here is my second derivative that I'm going to be plugging into, and we're just interested in the sign, positive or negative. All right, so when I plug in a number that is to the right of the largest one, so to the right of negative 0.63, I could plug in a number like x equals 0 into that second derivative. And I don't care so much about the actual answer as just the sign of the answer. So that one's positive. That tells us that the original function on that region will be concave up, like a happy face. Maybe not the whole happy face, could be the left half or the right half, or maybe both, but concave up on that region. And when I plug in a number between negative 0.63 and negative 2.37, like negative 1, for example, would be an easy number to plug in. Plugging that into that second derivative, should get a negative for that one. So that tells us that the original function in that region is concave down, so like a sad face on that region. Again, maybe not like the entire sad face. It could be the left half or the right half of the sad face, but like a sad face. And then when I plug in a number that is left of negative 2.37, like maybe negative 3, plug that into that second derivative, you should get a plus. And that tells us that on that region, the original function is concave up, like a happy face. All right, so now I can summarize the answers I have from my second derivative here. We would say that the function is concave up on two different intervals here, negative infinity to negative 3/2 minus square root of 3 over 2, or perhaps you want the decimal approximation there. And then the other interval where it's concave up, like a happy face, is negative 3/2 plus square root of 3 over 2 to infinity. The function's concave down on the interval between those two values. And then because the function changes concavity at those points, those are both the location of inflection points. And so inflection points are xy points. I'm going to just give the decimal approximations for these. So we have one of them at negative 3/2 minus square root of 3 over 2, or approximately negative 2.37 comma. I'll leave the y coordinate blank for a second. And the other one at approximately negative 0.63, comma, and leave that y-coordinate blank. All right, and the reason I've left those y-coordinates blank is that I need to go back to the original function over here to figure out those y-coordinates. So if I want really exact values for y-coordinates, I'm going to plug in my exact values for those inflection points and then round at the end. Let the calculator handle these messy decimals with lots and lots of digits of accuracy and then round at the end. Okay, so when I plug in those values, I didn't plug in negative 2.37. I let my calculator use the negative 3/2 minus square root of 3 over 2. I just typed that in to my table feature on my calculator, and then I looked at what I got for the y-coordinate, and rounded that answer. For that y-coordinate, I got about 0.03. And then when I plugged in negative 3/2 plus square root of 3 over 2, I got about negative 0.07 for that y-coordinate. So I'm going to go back over here and put those into my points that I have over here. Okay, so I have a whole bunch of information now that I can use to think about the graph of the function. I'm going to go ahead at this point and put my graph into some graphing utility. So graphing calculator or Desmos. I'm going to pull up Desmos here. Okay, so I've graphed the function in Desmos, and you can see that there is some behavior of the function that's maybe a little bit hard to see when you just graph this in the usual kind of negative 10 to 10 in the x direction and y direction. So I really can't see the changes in concavity that the calculus told me about. So I'm going to go ahead and zoom in here a little bit, and you'll notice that you can see a little bit better what's actually happening there. So from my calculus work, I know that I should have a point where the function has a minimum value at about x equals negative 0.3. So approximately right here, I have a place where I should expect there to be a minimum value. That was a little bit hard to see from the window I started at. Another place that's important is that I found from my calculus work that there's a maximum value at about x equals negative 1.71 and y equals about 0.04. So in the beginning window that I looked at, I really couldn't see those places. The other points that it's difficult to see in the original window I had was the places where I have some concavity changes. I'm going to go ahead over here and just type x and y coordinates of points. I typed the x and y coordinates of the 2 points that I found for inflection points, and you can see that if you zoom in around those points, you can maybe see the concavity change. It's a little bit hard to see around the point that's here at about negative 2.37, 0.03. You can definitely see that on the right side of that point, it appears to be concave down, like a sad face. It's hard to tell from the graph, though, but that on the left side of that point, it is concave up. Maybe if you zoom way in, you might be able to see that it's concave up like a happy face on that side. We can also see from this graph that it appears there's like a horizontal asymptote for the function where as x approaches negative infinity, the y values appear to be approaching 0. You could verify that by plugging in some numbers like we did for limits to think about the limit. All right, so I've used the graphing utility to help me. I'm going to go ahead and sketch a graph of what I see and label those important points. Okay, so I've set up XY coordinate system here, and I scaled my axes differently. Part of the reason I did that is that the y coordinates on all of these points that we found were very, very close to 0. So I made my y-axis very, very big so we'd actually be able to see those points. My x-axis, I need to go to at least negative 2.37. That was where we had an inflection point. So I made my x-axis go a little bit past that, maybe even a little bit beyond that, so we can see the end behavior of the function. But I didn't want my graph to be so wide in the x direction that we couldn't see the information. So now I'm going to put on here the XY coordinates of all those important points, the maximum, the minimum point, and the 2 inflection points. Okay, so I've labeled all of the points, the important points that I found from my calculus work here. And these are decimals, so it's a little bit hard to plot them perfectly unless you're using a computer to do that. But notice a couple things that I did here. I have two y coordinates on these 2 points that are above the x-axis, and I made sure that I plotted the one with the slightly bigger y coordinate a little higher than the one with the slightly lower y coordinate, and then the same thing with the y coordinates for these two that have negative y coordinates, my inflection point and my minimum. All right, and then I'm going to go ahead and sketch in the function. So I'm going to look at the information I had above. I'm going to look at the graph that I see on my Desmos or graphing calculator, and I'm going to be sure that when I graph it, I can show the concavity changes in the increasing and decreasing. So I tend to do that in pieces, kind of between these important points of the graph. So I'm going to start on the right side of the graph, actually. So I know that I have a point that's a minimum, and the function should be increasing on the right side of that. I'm going to use my graphing calculator to help me see that that curve goes through the origin, and I have a point there, and then heads upward. I know the function should be increasing and concave up in this region. Okay, and then between my inflection point and the minimum, the function should be concave up still, but that function in that region is going to be decreasing and going down. So still like a happy face in that region, but there's a little dip down to that minimum point. All right, and then between the two inflection points, so between the 2 points that I've labeled IP, between those 2 inflection points, the graph should be concave down, like a sad face. I also know that I have a point that's a maximum, so that should be the highest point in that region of the graph. Maybe you can use your graphing calculator to see that there's a point here at -1 where it crosses through the x-axis. And then I know that left of my inflection point, the graph should be concave up. This is what's really hard to see on the graphing utility. I can also see from the graphing utility, I could plug in numbers and a table of values, that there appears to be a horizontal asymptote, the limit as x approaches -infinity of the function is 0. So over here, if you can't tell from the way you drew it, maybe you go ahead and label that that is concave up in that region. And certainly if I made my y-axis a lot bigger, it might be easier to see that, but if I zoom out sort of on my y-axis direction, it might be easier to see that it's concave up on that region. But this is an okay sketch, and I would say that if you're asked to sketch something that shows all these things and you feel like what you drew doesn't necessarily show that it's concave up, just label that on the graph. When there are parts of the graph that are really close to each other or not very exaggerated in terms of how much like a happy face or a sad face they might look, it might be hard to see that, but just go ahead and label that on your graph. All right, so this is a really long problem doing all the stuff, but kind of ties together everything we've really done in this unit. We'll look at another problem like this in another video.